In this lecture, we construct an explicit 2 isogeny. So say we are given a curve like this, y square is equal to x cube plus ax square plus bx. And say it factorizes like this, x minus alpha 1, x minus alpha 2, x minus alpha 3. So this alpha 1, alpha 2, alpha 3 are the roots. So the roots, you write it as pi as alpha I 0. So for I equals to 1, 2, 3. So for 1 you have alpha 1, for 2 you have alpha 2, and 3 you have alpha 3. So obviously once you plug in alpha 1 here for x, you will get 0 here because these are the roots. If you plug x equals to alpha 2, this term will become 0. So you again get y square as 0. So we are looking at these points which have two torsion, that is 2p is equal to the special point on our elliptic curve. So this 2p equals to the special point is just equal to p is equal to minus p, and that means minus xy is equal to x comma minus y. So this is the negation of a point on an elliptic curve. So if this thing holds, then the only points where this will hold is precisely where y is 0. So this y is 0, you can see y is 0 here for the roots. So for the roots we have the condition that 2pi is our special point or 0 on the curve. So the condition is satisfied by our roots. So an assumption we are going to make is that there is a rational root for the given curve. So there is some root out of the three, and say this one root out of alpha 1, alpha 2, alpha 3, this root is rational. Now this rational root would be an integer precisely because for our elliptic curve which we take here, this a is an integer, this p is also an integer, and when you plug this x0 in here instead of x, so since this is a root, rational root, this y will become 0. So you will have this equation with all integers here, and therefore you have to solve this in terms of integers. So therefore this rational root will become an integer. So this involves you still have to prove this, that if you're plugging in a rational root here, it is just an integer, but you can easily see by putting it in this equation. So this x0, this is an integer since the curve has integer coefficients, precisely because a and b are integers. Now we can do change of coordinates. We can move this point, so our root will look like x0 comma 0, just like here, because it's a rational root and it has order at least 2 as we have seen here. So we can move this point, change the coordinates to origin 0, 0, and still again you will have 2t is equal to our special point on the curve, that is a 0 on the curve. So this is our special point. So the new equation will look like this: y square is equal to x cube plus ax square plus bx. Again a and b are integers. We have just changed the coordinates from x0, 0 to 0, 0, and we have said that this x0 is actually an integer. If you start with a rational root, it will become an integer. So now we come to our story which we want to talk about here. So we want to construct an isogeny from, say, our given curve C here to some green curve C again. So from this elliptic curve to this elliptic curve. So from here to here you get another curve. So instead of A and B in white, we have A and B in green. So this green A and B you get from this green A here. This is minus 2A, this A here minus 2A, and this B is a square minus 4b, which is this a, and this b is this b. So this is the relationship we get. So this, and from green curve we can move to the red curve again by the same procedure. Now you have x cube, now you have a in red and b in red. So this red a is 4 times white a, which we take from here. This red b is 16 times this white b, which we take from here. Actually we repeat the same formula for the red curve, because this red a is minus 2 times green a, but green a we have taking as minus 2a here. So plug this in here and you get plus 4a, which we write right here. And this red b, same formula. So red b is green a square minus 4 green b. So same formula here, we carried it here but in terms of green, but this green a is minus 2a, so you get 4a square. Instead of b you have a square minus 4b, plug it in here, you get 16b. Same thing as here. So this, if you get this, you have your red curve. Now this red curve actually is isomorphic to our white curve, and this isomorphism you can see by this replacing xy with 4x 8y. You can see this directly here. So instead of y square, if you put instead of y, if you put 8y, you will get 64y square, and instead of x cube you put 4x, you get 64x cube. So again you have x squared here, which will give you 16x square. 16 times 4 will give you 64, so this will become 64ax square. And then again x we are putting as 4x, you get 64bx. Now you cancel 64 out and you are left with the same equation as this. So this is the same equation here. So this red curve is same as the white curve if you change the coordinates again. So what we are going to do is to go from the red curve to white curve, you have to divide by 4 the x coordinate and divide by 8 the y coordinate, and this we will keep in mind later on. So since this is just multiplication, their group of points is the same. So the rational points on our red curve is same as the rational points on the white curve, because you can just interchange them by multiplying by 4 and 8 or dividing by 4 and 8. So now we define isogenies. So we are going to define one isogeny which goes from white curve to green curve, just like this. This isogeny is going to be, say, phi. Then we are going to define a dual isogeny which is going to be psi, and we compose these two, we get a isomorphism, because here we just have to to go from this red curve to white curve, we just have to divide the coordinates by 1 4 and 1 8, which we will do later. So this is just an isomorphism. So we can go from white curve to green curve, and from green curve we can apply this psi and go back to white curve. So this is red here, which is same as the white curve via this thing. So red is same as the white curve. So first isogeny is going from the white curve to the green curve. So you take points xy on this curve and they will get mapped to y square by x square, then y x square minus b over x square. So this is our rational map, x and y on the green curve, and this is just the special point on the green curve. If this xy to start with is a special point, or this xy is 0 0, that is t. So the kernel of this map contains these 2 points, because these are the 2 points which are getting mapped to this O. Now in the same process we can define a map from green curve to the red curve, and we have seen this holds if you just take the x coordinate, divide by 4, and y coordinate also divide by 8. So this will hold, as we have seen here. So we will again have an isogeny from the green curve to white curve or red curve, and from red curve you just do this division, you go back to white curve. This is just a constant change. So again now we are taking points xy on the green curve. You have the same formula like this, and you have the special point if xy is the special point on our green curve, or it's a torsion point. So essentially the same idea, but now we are talking about special point of white curve. So we will show 2 things. First of all, we will show that this isogeny makes sense, and obviously if this isogeny makes sense, then this isogeny will also make sense, because they're exactly the same isogenies. And then finally we will divide by 4 and 8 to get to this white curve C. Another thing we want to show is that this psi and phi are dual to each other. So dual to each other means that if you compose them and you compose them again back like this, you get some n times some point. So you will get a explicit 2 torsion. So this we have to show. So one, we have to show that this is an isogeny. This makes sense. So we will not show the complete proof. The complete proof of this is an isogeny can be found in this book, Silverman and Tate, Rational Points on Elliptic Curves. So page 84 and 85, chapter 3. So you can find this on this book. But we will say that these show that these two maps make sense, and this is equal to 2p and this is also equal to 2p. So to show that these points actually make sense, we have to show that these 2 points lie on the green curve for this to even make sense as a map. So therefore this is our green curve, and this we have to show is equal to y square. So that is the equation of the green curve. Y square is equal to x cube plus ax square plus bx. Now you take x common, out, and instead of a you put in minus 2a. So this is the substitution we had done before. For green, a is equal to minus 2 white a, and b is precisely equal to we had done as a square minus 4b, and that's what we put here. And then you just do the cancellations and everything, and you will get y square. So this map does make sense. So this is our, say, green x, and this is our green y, and if you do a rational map like this, this map makes sense. You lie on the green curve. So this is a proper map between two you can say algebraic varieties. And there's a little bit more we have to do to show that this is an isogeny, but you can see that in the book in chapter 3. So here we will stop. So since this makes sense, we have exactly the same map here. You see y square over x square, y x square minus b over x square. So this map from the green curve to the red curve will also make sense. So now we will show this part. This psi composed with phi is 2p, and in a similar way you can show this part, that phi composed with psi on p is 2p. So our 2p is given like this. So you take a point p which is xy lying on the elliptic curve, you double it. This is the formula you get using that chord tangent method. So now you apply phi to this point xy. We have to show that this, you apply phi to the point and then you apply psi, you get 2p. So that you should get this formula. So first you apply phi to it, you just copy this. For the x coordinate you have this, for the y coordinate you have this. So that is just copied. Now you apply psi to it. You know the x now is this portion and the y is this portion. So x is y square over x square. So instead of x square, you write y square over x square. Plug this in here. This square comes right here. For y square here, you have this entire thing. So y times x square minus b over x square, and this square comes here. Similarly here, for x, you write this entire thing. For y, you write this entire thing. Again for x, and we had set b is equal to a square minus 4ab before. So this b was a square minus 4b. So that's what you write it. So this 4 and 8 come from the fact that we have to go from the red curve to the white curve, and for that we said that we have to divide x by 4 and y by 8. So the x coordinate we have divided by 4, the y coordinate we have divided by 8. So you get this y4 here. So this y4 is nothing but x square times x square plus ax plus b square, because our elliptic curve we started with was this, x square plus ax plus b. So y4 is just square of this, and then you make the substitution here and simplify it. We will get this result right here. So we have been able to show this portion. Similarly, you can do the same computation by first using psi instead of phi, and you will still get 2p. And this you can see because these formulas are kind of symmetric to each other. So same thing you can do here. You will still get 2p. So what have we done? So we have constructed two isogenies going from one curve to another. So from white curve you go to the green curve using this map phi, then you apply map psi, you come back to the white curve, and by applying phi and then psi you land back in the curve C. This is equivalent to a map going from C to C and doubling the point. So it is same as doubling the point. So first you apply phi and then you apply psi. It is same as doubling the point. And you can see this going from green to white and then back. So these two isogenies are called dual to each other because they're producing a distortion point here. So this explicit 2 isogeny will be used in completing the proof of the Model's theorem.